Inverses. So in the last video, we took our quadratic and we found the inverse of it, and we graphed both the original quadratic and the inverse. We talked about how the original passed the vertical line test and so therefore was a function, and how the inverse did not pass the vertical line test and therefore is not a function. So the question that we need to answer is, how can we change the domain of the original function to ensure that the inverse is also a function? So let's look at our original quadratic and split it up into two different sides, divided at the vertex. So the right-hand side I made pink, and the left-hand side I made purple. Now, if this is a reflection about the line y is equal to x, then the pink side would create the upper part of the relation of the inverse, so the pink side. So I'm going to match the colors here. The purple of the original would match the purple of the inverse. So therefore, if we want the inverse to also be a function, we want to restrict the domain of the original and essentially remove that purple side. So what we're going to do is we're going to say that we only want x is greater than or equal to 0. That would make the original not have the purple at all, and therefore the inverse would also not have the purple. That means that our inverse is now a function. Our next question. Find the inverse of the function by identifying an appropriate restriction of its domain. Again, we're given a quadratic. In the last example, we identified that at the vertex, we need to restrict the domain. So that means we need to find the vertex. The vertex, remember, for a quadratic, is in vertex form. If we look at the question that we're given, we can actually factor this. Numbers that multiply together to get 16 and add together to get 8. So we can change our function to be x plus 4 squared. So this is our vertex form. And from vertex form, we can identify the vertex. So normally it starts at 0, 0, but now our vertex is shifted to the left by 4. So that means our vertex is negative 4, 0. The y value hasn't changed because there's no k value shifting it up or down. If I was just going to do a sketch, my graph would look something like this. So the question is how am I going to restrict that original one to make sure that the inverse is also a function? Well, what we're going to do is we're going to knock off the left-hand side. So that means we're going to restrict the domain by saying that the domain has to be x values greater than or equal to the x value of the vertex. Example 4. Find an equation of the inverse function. So let's first start with what we know about our original function. This is a radical, so that means that our graph is supposed to go up and to the right in its parent function state. It's also been shifted to the right by 2. So if I do a sketch, it looks like this. To find the equation of the inverse, we're going to take the original one, and we're first going to replace f of x to be y. Then we're going to switch x and y. So we get x is equal to the square root of y minus 2. Then we will solve for y. So when we solve, we're going to take the square of both sides, and then we'll add 2. So we have a new equation. Now notice that our new equation is a parabola. So that means that we have a parabola that's shifted up by 2. If we were to graph this, it would have both sides. But our graph cannot actually have both sides because then it wouldn't be the inverse of our purple function there. So that means that we need to have some sort of restriction. Where x is greater than or equal to 0. Now let's look at the domain and the range of the original function. So purple. Our domain is x is greater than or equal to 2, and our range is y is greater than or equal to 0. So that means that when we find the inverse, our domain and range are going to swap. So let's see if it makes sense. Our inverse is our pink. The domain is x is greater than or equal to 0. That is true. And our range is y is greater than or equal to 2. That is also true. In summary, the domain of the original is the range of the inverse, and the range of the original is the domain of the inverse.